Hello, everybody. This lesson is about summation notation. So in this lesson, we will learn to write Riemann sums in summation notation, and we'll also write the definite integral as a limit of Riemann sums. In pre-calculus, you learned that the summation symbol, or sigma, the Greek letter sigma, capital sigma, that notation is an efficient way to express a sum. For example, if you were to add 1 plus 4 plus 9 plus 16, you can condense that into an expression in summation notation. It's the sum from k equals 1 to 4 of k squared. So it's just an efficient way to write out what could end up being a very arduous and cumbersome sum. So we're going to use that to talk about area under the curve today. So to refresh what we did in lesson 6.1, which was computing Riemann sums to estimate the area under the curve, we will first look at this graph, use summation notation to express a Riemann sum first. We'll deal with definite integrals later on in the video. So first we're looking at this graph. This is actually the graph of x squared. We've got points at 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. The first question is calculate the left Riemann sum on the interval 0, 4 with 4 partitions. So 4 partitions means that if I take the interval 0 to 4, so 4 minus 0 divided by 4 is 1. So my delta x is going to equal 1. So that should look pretty clean. We got from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So left Riemann sum means I'm orienting myself with the left side of the base of the rectangle. So from 0 to 1, I'm taking the point 0. From 1 to 2, I'm taking the point 1, 1. Okay, and so forth. From 2 to 3, I'm taking the point from 2, 4, and then horizontally from there. And then at 3, 9, I'm taking the height of 9. Okay, so that's going to be my, and this isn't like a great drawing, but that's going to be my left Riemann sum. All right, so I'm going to just kind of color code this in blue. So we've got this will be a rectangle with an area of 0 right here. This will be an area. This will be another rectangle, and another rectangle. I'm really trying to make this like not hideous, but I'm doing my best. Okay, so for the left Riemann sum, we've got a width of 1, and our first height is going to be 0. So 1 times 0. Our second height is going to be 1, right? So 1 times 1. Our third height would be 4. So 1 times 4. And then our last height is going to be 9. So 1 times 9. And you can also write that as 1 times 0 plus 1 plus 4 plus 9. That's another way you can express a Riemann sum, because the base of the rectangle is going to be constant for all of these area computations. So we've got 1 times 14, which is going to be 14. So that's our computation there. We can also write that in summation notation. So this is going to be the sum from what x value we start at, which is 0. So we can say k or n. I'll use k just because it was up here and we're going to be using it for the rest of the lesson. You can really use any index you want, but I think for clarity, it will just be consistent with the k. So k equals 0 to 3, right? Because the last x value at which we took a height to calculate the rectangle area was x equals 3. So the sum from from k equals 0 to 3 of k squared times 1, right, which was our delta x. Okay. So it's a sum of these areas. This was our height. The k squared was our height, and the 1 was our width. Big width. Okay. All right. So that is how we can write our left Riemann sum in summation notation. Let's do the right Riemann sum now. So I'm going to change colors for that one. So calculate the right Riemann sum on the interval 0, 4 with 4 partitions. So still the same delta x, but I'm going to orient myself for each sub interval. I'm going to orient myself to the right. So instead of starting at 0, 0, I'm going to start at 1, 1 and make my rectangle, draw it to the left. So that's going to be my first area, my first rectangle that I'll compute the area of. And then for my second rectangle, I'm starting at the right side of that subinterval, which is 2. So we got 2, 4. Then 3, 9. And 4, 16. All right. So we learned in the first lesson in this unit that the blue is going to be an underestimate because we have a graph that's concave up and increasing. So a left Riemann sum is not going to cover all the area. And our right Riemann sum is going to be an overestimate because you can see pieces of that rectangle poking above the graph. So this will be an overestimate. So if we calculate the right Riemann sum, our width is going to be the same, but our heights are going to start with 1 instead of 0. So we're going to have 1 times 1 plus 1 times 4 plus 1 times 9 plus 1 times 16, or you could have written that as 1 times 1 plus 4 plus 9 plus 16, which comes out to 1 times 30. So that Riemann sum, that right Riemann sum is going to be equal to 30. Okay, very different numbers, pretty not great approximations on both directions, but we're connecting the summation notation right now, and then we'll talk about how to get a better calculation for the area. So in summation notation, we're still taking the sum, but instead of starting at k equals 0, we're starting at k equals 1, and then we're stopping at 4, because those are the heights that we're taking. We're taking the height of the function at 1, 2, 3, and 4 instead of at 0, 1, 2, and 3. Right, and then everything else is going to look the same as the left. So we've got the sum from k equals 1 to 4 of k squared times 1. Again, height, width, the sum of these areas, right? 1 times 1, 1 times 4, 1 times 9, 1 times 16. Okay. This video that I have the URL to is a really great visualization. We're going to show it in class, but I'm not going to show it now because you can always kind of look at it. It's the folks over at Flipped Math. They have a really good visualization of this. So if we look at our graph and the Riemann sum approximations, we know they're not great. You know, we're missing a lot of area with our left Riemann sum, and we have too much area with our right. So what this video is going to help you visualize, I'm just going to sketch it because, you know, I think I'm not going to do it justice, but I think the concept will come through. If you had the width of your rectangles be much, much, much smaller, so instead of 4, maybe you have 8 rectangles, you'll notice that you get a lot closer to the area under the curve. Okay, so the smaller the width of your rectangle, so 1, 2, 3, 4, 5, 6, 7, 8, the smaller your rectangles, I'm sorry, not the smaller your rectangles, but the smaller the width of your rectangles, the better approximation you're going to get. 1, 2, 3, 4, 5, 6, 7, 8. So what we're going to kind of visualize in this video, and a really key element of this unit, is if you had infinitely small bases, you're eventually going to get the exact area under the curve. Because if you can visualize this getting smaller and smaller and smaller and smaller in terms of the width, it will eventually be exactly the area, right? So the smaller the width of your rectangles becomes, right? So you have infinitely many rectangles and infinitely tiny widths, you're going to actually get the area. You're going to get better and better approximations until it actually is the area, okay? So what we call that is the definite integral. The definite integral is actually the exact value. So let me move the camera so we're covering the rest of the page here. So what is the definite integral? I think of the definite integral as definitely the area. It might be a silly way to think about it, but I think it helps. Definitely the area. So instead of being an approximation, the definite integral is definitely the area of the curve under the curve. So the formal definition, given a function f of x that's continuous on the interval a to b, we divide the interval into n subintervals of equal width x, so delta x. So n is going to get infinitely large, and delta x is going to get infinitely tiny. And from each interval, we choose a point, and then the definite integral of f of x from a to b is written this way. The integral from a to b of f of x with respect to x is equal to the limit as n, again, your number of rectangles, approaches infinity from whatever your index of summation is, which will usually start at 1, to n of f of whatever function you're starting, whatever x value, the value of the function at whatever x value you're starting at, plus x times delta x, right? So the analogies are dx and delta x are kind of similar here, and you still have the function here. So you can express a definite integral as a limit of Riemann sums and vice versa. Okay, breaking down the symbols here, this long s is the integral sign. It's just a stylized s. Just think s for sum, right? That's what integrals are. It's a sum of areas. F of x is the function being integrated. A is your lower limit of integration, x equals a. So in our example here, it would be 0. And then b is your upper limit of integration, x equals b. So again, in our example, it would have been 4, because in both our left and right estimates, we took the estimate from 0 to 4, x equals 0 to x equals 4. So these are x values here, where you start, where you stop. Okay, and then dx tells us that x is the variable of integration. So that's telling us that we are taking the integral with respect to x. Please don't forget to put this on your integral. It's very important. Okay, and then looking over at the notation on the right side, sigma is the Greek letter sigma, also stands for sum. So these are sort of parallel symbols here. Delta x is the width of each subinterval, and it's going to actually be computed by the formula that we used in the previous lesson, b minus a over n. N is the number of intervals, again, infinitely many in this case, and that's why our n is approaching infinity. And then k is the index of summation, which is what we're counting by. Sometimes you'll see I or j. Again, I'm just using k just to keep things consistent, but you might also see, I equals 1 and x sub I, etc. So, or j. So just be aware that just because you don't see k and you see a different letter, it's the same idea. Okay. Okay. So we're going to do a couple of examples, and then the rest of this would be classwork, homework, and I'll post a key in our learning management system for the homework here. So we're going to go both directions. We're going to express the limit of Riemann sums as a definite integral, and then we're going to go the other direction, expressing a definite integral as a limit of Riemann sums. Okay. So we have our familiar limit as n approaches infinity of the sum from k equals 1 to n of square root -2 plus 5k over n times 5 over n. Okay, so we're going to annotate this a little bit. All right. The -2 is under this square root, right? So this is actually going to be our lower limit of integration, or our a. This is going to be our a because it's added to the expression that represents x. Okay. Our delta x is 5 over n. So that's our delta x, 5 over n. Okay. And so this term here is going to be our delta x times k, and k is sort of analogous to your x, right? So what we can conclude from this information is that we have our lower limit, which is -2, and our b is going to have to be our lower limit plus 5, which is 3. Because if you think about it, since your delta, move up here, since your delta x is equal to b minus a over n, right? That is telling you that your, since your delta x is b minus a over n, your b minus a is clearly 5 in this equation. And we already established that a is -2. So b minus -2 equals 5. b plus 2 equals 5. So b has to be 3. So that's how you can figure that out. But the shorthand would just be, okay, here's my a value. I can add 5 and it's 3. We're done. We're good to go. Okay. And then the last thing we need to convert limits, to convert the limit notation into an integral is f of x. All right. So in this case, we have the square root of, this is again our lower limit of integration. This is our delta xk. So all of this whole function is just square root of x. Okay. So we write it as a definite integral as the integral from -2 to 3, a to b, because a is -2 and b is 3, of square root of x. And then don't forget your dx. And then that's it. Okay. So you're looking for your function, what your function operation is, your a value, which will usually be something added to the blank k over n within the function. And then we're adding our delta x times our k. And again, our k is analogous to our x. Okay. So we're going to go the other direction, example 2, express the definite integral as a limit of Riemann sums. So I have the integral from 1 to 3 of 1 over x delta x. Okay, so we know that our a is 1 and our b is 3. So for our delta x, it's going to have to be b, oh, sorry, well, our delta, it is b minus a over n, might as well put that in there. So 3 minus 1 over n is 2 over n. So our delta x is going to be 2 over n. Okay. So we're going to follow the same procedure. Well, we're going to model, or sorry, we're going to use this model to write out our limit. So we can write it as, this will always be consistent limit as n approaches infinity of the sum from k equals 1 to n of this function. So we know the function is 1 over blah, okay? And that blah is going to be a plus delta xk. So 1 plus 2k over n, okay? And then we have to multiply it by our delta x, which is 2 over n. And that's it. Okay. Sometimes I think about this as function composition, right? You're putting your a plus delta x k inside the function that you're trying to replicate in there. So if that helps, you can think about it as sort of a composition. Okay. So everything else, this key will be posted. The key to the homework problems is going to be posted. But I hope this video helped. If you needed it, I hope you have a great day, and I'll look forward to working with you again soon.